Pablo's Learning Center. Today we're going to learn about how the model of the atom has evolved through time, starting with Democritus. Democritus introduced the idea that atoms were the building blocks to all matter. He believed they were indestructible and that there were different types of matter because of the types of arrangements, sizes, and shapes. Later came Dalton, whose ideas can be summarized into 5 key points. All matter is composed of atoms. All matter of the same elements are of the same size and mass. Atoms can be subdivided, created, or destroyed. Atoms of different elements can combine in simple whole number ratios to form chemical compounds. And in chemical reactions, atoms are combined, separated, or rearranged. Thomson discovered the existence of particles smaller than atoms, called electrons, that were the negative charge in the positive nucleus. His atom was called the plum pudding model. Later came Rutherford, who did a gold-foiled experiment where he discovers that the atom had a nucleus and it was made up of mostly empty space. Then came Bohr, who developed the model of the nucleus or electrons encircle the nucleus in orbits and can also move into different orbits if energy is added. His model was called the planetary model. This model was the one that we use today. The limitations of Bohr's atomic model were that it was seriously limited when applied to other atoms, only good for hydrogen models, because it was created in 1913.
Welcome back. This is Bohr's model, and here you can see how an electron goes from an excited state to the ground state. What happens here is that as the electron goes lower and lower, photons of light are released, and that's why we have this. And then, if you want to see why they're different colors, it depends on the amount of energy released. It's red because very low amounts of energy have been released, and it's blue because high amounts of energy have been released, because the change is more drastic. And that's the atomic emission spectra for you.
Continuing on what my classmate Chamorro said, when atoms lose an electron, they become a positive element because they have one more proton than electron. And for isotopes, they are atoms with the same atomic number but different mass numbers due to a change in the number of neutrons, which could be shown in there being 10 neutrons and 9 protons, and 9 neutrons and 9 protons, but it's still the same element. But since there's one more neutron in the other one, it has an increased atomic mass.
Thank you, Alfredo. Now it's my turn. Okay, so first, alpha decay is when an atom with a big nucleus breaks down by ejecting an alpha particle. And what happens here is that the atomic number changes by 2 numbers down. So if it's 92, it changes to 90. And the atomic mass changes from 4 numbers down. So if it was 238, it changes to 234. Then beta decay is when an atom with too many neutrons breaks down by ejecting a beta particle, which is a high energy electron. And what happens is that if you have 6 in the atomic number, it changes to 1 up. So a proton enters the atomic number and it becomes a 7. And then the gamma radiation is when it accompanies most nuclear reactions as the excited nuclear state relaxes and releases a large amount of energy. And in that state, nothing changes. It stays the same, the atomic mass and the atomic number. And remember, gamma decay can't occur before having either alpha or beta decay.
Half-life is the time required for a quantity to reduce to half of its initial value. For example, the initial value is 100. When one half-life has passed, it becomes 50 grams. Later, when 2 half-lives pass, it becomes 25 grams. And when 3 half-lives pass, it becomes 12.5 grams. So after each half, the value decreases. Electron configuration in base electrons. You can see the different types of configurations to see the electrons in each atom. For example, we can use electron configuration as it is in here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. That is electron configuration. But another way in which we can see the electrons in an atom is by using the orbital notation, which is like this, and where you can you can only fill one up after the other one has been fully filled up. For example, you can't fill up 3s before filling up 2p. You have to start by putting one in each, and you can't have two before the other two have one. Electrons and atoms is a noble gas notation. As we can see here, the element is arsenic, which is located here in the periodic table, and the noble gas that's before arsenic is argon. So we use argon, which has already 18 electrons, and then we add the remaining 15 electrons to make it arsenic, which is 33. We can see that it also has 5 valence electrons, because in the periodic table, as we can see, here it says 5a, and we can see that it's arsenic.
Nuclear fission is when a large unstable isotope is bombarded by a high-speed neutron and splits the isotope into smaller particles with a large amount of energy being released. As we can see in this model, a neutron goes really fast and it crashes against the atom, and then a high amount of energy is released. And the other one is nuclear fusion, where it's when atoms of tritium and deuterium unite under extreme pressure and temperature to produce a neutron and a helium isotope. Much more energy is released by fusion than by fission, and we can see in this model that deuterium and tritium combine in fusion, and then it releases a lot of energy.